Yeah, this talk is, it will not be very technical. It's a recent journal publication that I thought might be interesting to you guys as well. So I will take it a little bit more on the high level and discuss some trends and some reasons for which I think that actually the outlook of using accelerators in database workloads actually is very positive. So just to start with a little bit of context and to make sure that we are all on the same page. So when you will see me there, but it's going to be interesting. So when you think of database queries, I think maybe hands up, like who doesn't remember anything from their introduction to databases from their bachelor? Like, is there anyone? You can, okay, I see a few hands. So let me go through this very quickly. So in the database setting, maybe you have a query like this where you want to list all suppliers from a region who have some kind of part that they're supplying in stock. And then you will express this in SQL, which is a language to interface with the databases. But what is important for this talk is it will result in a so-called query plan. And here we're talking about the physical query plan because it actually defines how the different operators are implemented. But what is important here is you have something which is a supplier table. So this will be the data set which describes the suppliers. You have something which is called the supply data set, which would be, let's say, the inventory at each of these suppliers. And then you're doing operations like joining, where you're bringing in data from both tables, and then finding the ones where the supplier ID here and the supplier ID here is the same, constructing some new tuples, filtering here by city, state, and part number, and then finally outputting a name. The point here is that this query plan looks quite abstract, and that's a good thing. What this really says is just describes how data flows through this execution plan. You can do things like here, you can choose an algorithm, which for instance is called nested loop join. You can do filtering here on the fly, which means that you're actually not buffering the whole data set before outputting these results. This is going to be fun if we're gonna lose half of the screen. Okay. So what is important here is the data. You can imagine it as streaming through this query plans, right? So you have, this is a large file here, and you're reading things through like this and this. What this also allows you by the rules of relational algebra, and if you're interested, we can go more into detail on that or refreshing your memory. But what is interesting is you can actually push down these filters beyond the joins. So if you wanted for some reason to first filter all the suppliers by city and then only join on the remaining ones, you could do that. And this is what is called query optimizing or query planning, where the database will do a lot of internal computation, figuring out based on statistics and samples of the data, whether it makes sense to first bring both tables, join them, and then filter, or whether it makes sense to filter here. What is also interesting is this plan actually can be seen as a distributed execution plan as well. So this data could be on different machines. You could use network links here, or you could do this all in the whole machine. So I just wanted to kind of bring your attention to the fact that when we talk about databases, actually there's a very smooth transition from running inside a single machine where all of this is on a single disk, or running kind of a distributed database where all the data sources are sitting on different machines. And then the other thing that we need for just to be on the same or talk about the same things is that when we think of databases, there's two fairly different use cases for them. So one, and the one that we're going to focus on, is called online analytical processing, which deals with large data sets, and the result or the goal of querying is to extract some insight. So you can think of this as running your monthly reports for all the sales of Amazon, but you could also think of queries which, for instance, try to find the most sold items on the whole Amazon sales from last month, or the items which bring in the most profit, and so on. So the point here is that the workloads are read mostly or read only. So you have your data set, let's say from last month, it's a terabytes of sales data, and you're running relatively compute-intensive queries on it. In comparison to this, or in contrast to this, there is the online transaction processing. Maybe this is the use case that you often think of when you think of databases, which is more the, you have your web store, and then you're handling queries like putting things in a shopping basket and checking out, handling the payment, so on and so forth. These databases are designed a little bit differently from the analytical ones. They make heavy use of indexes because they need to do a lot of random lookups, and they have reads and updates intermixed. So for the remaining of the talk, think about this one. Whenever I say database or analytics database, it's this type. So you have a lot of data. The data will be sitting either in main memory or on a flash or disk, and it's being brought in at a large volume, and we're trying to execute some kind of compute-intensive query on it. Okay, so if you look at databases, this has been a very large market. So some estimates say it's been like $25 billion in 2018, and much of this is actually happening in the cloud. So if you look at Microsoft, they are offering a lot of like Azure SQL solutions where you are actually outsourcing the database administration to the cloud, and you store your data there. So the question is, could we specialize machines to these workloads? If you could specialize your machines to these database workloads, you could offer them, service providers could offer them cheaper and increase their profits, or decrease the prices overall for everyone. As it turns out, the idea is far from new. So in the 70s, people were already thinking of this, and this is from a paper from Ohio State called the Database Computer, or paper, well, a project. And as you can see, they were very ambitious. They said, so they were developing a machine which is built for database use cases, and they wanted to run 10, or they said it's only going to be economical if you run it for at least 10 gigabytes of data, which I guess in the 70s was a very, very large number. So what they designed is something which looks like this. You don't really need to go into the details. They have a bunch of custom microprocessors here, and the data is moving in some patterns. They really designed this from scratch. So they designed the microprocessors which do exactly these things. They use the newest and coolest tech available at that time. So they use magnetic bubble memories and charge coupled devices. And I have to admit, I had to look these things up when I was reading this paper, because I honestly didn't know what magnetic bubbles are. But in the 70s, it was the thing that they assumed it's going to revolutionize computers. Since you don't know what it is, or probably you don't know what it is, it didn't revolutionize computers. So what happened in the meantime is semiconductor technology took off. So transistors became let's say, the main building element of all the computer chips we have, and general purpose CPUs took over. So this project kind of, let's say, failed for the reason that semiconductor technology just became very cheap. In the 80s, there was another project which I think is very interesting from Wisconsin, and this was again building a database-specific machine, but this time with more, let's say, off-the-shelf components. So this was using a VEX multiprocessor system, but still assembling these things in a custom way. So these are all processors. It's a multiprocessor system. They're moving data around. They have some specific elements. But what happens with this system is that by the time they actually, let's say, created the hardware and wrote the software for it, the general purpose CPUs have been doubling their performance. So by doubling their performance by Moore's law, and essentially by the time they finish doing this, the other CPUs that you could buy, in the shop were so much faster that even the general purpose database machine was beating their specialized solution. So based on roughly on these two projects, people have decided that there's not much use for trying to specialize for database use cases, and this was actually true for a long time. So if you look at the way CPU frequencies were increasing up until the 2000s, you see this is an exponential growth. So this is a logarithmic scale here. So essentially, if you started building your database machine here, right, and your database machine gave you 10x speed up, and it took you 5 years to develop it, then if you just waited 5 years and bought the next CPU available on the market, you would get the same 10x speed up. So in some sense, here there was no point in trying to make a specialized solution because the general purpose CPUs were just getting faster. But then, of course, what happened is that at some point Moore's law or the Denner scaling started slowing down, and the machines were not getting much faster. So here, nobody was really, let's say, venturing into specialization because CPUs were scaling well. Then what happens here, there was an economic incentive to do specialization, but the cloud became kind of the ruling power. And what happened in the cloud initially is the public clouds were built on commodity hardware, right? So if you think of Amazon when it started out, all the machines there were not super fast, special purpose things, but they were off the shelf, run-of-the-mill machines. So in some sense, even though here people were already interested in using maybe the transistors differently, designing custom chips for big data workloads or data-intensive workloads, you couldn't really deploy this in the cloud because there was no economic incentive to have special purpose machines in the cloud. And then 5 years or so, we entered the era which I think of as a revival of specialized hardware. And what happened is other workloads appeared in the cloud, like machine learning, big data analytics, where people suddenly became very much bound on the compute resources that these machines had. So if you remember what happened at some point, people started, or Amazon started offering GPUs in the cloud. So suddenly you started having not only CPUs, but a little bit more specialized general purpose GPUs in the cloud. And then from there, Pandora's box opened. And nowadays we can imagine putting even more specialized devices. So if you think of TPUs, the tensor processing unit that Google has, or Microsoft's FPGAs, these are all happening. So I think we're in a space where it's interesting to, let's say, we can think of specialization, but it's also economically feasible to do it. And okay, you probably already heard my talk, so I'm gonna go quickly through this. Many people are choosing to specialize. So if you think of CPUs, they are very, let's say, very flexible, very general purpose. You can run anything in a CPU. But it's not very energy efficient, right? To execute a single instruction, you need to power registers, and you need to decode instructions, and you need to do a lot of heavy lifting to execute a single instruction. On the other end of the spectrum, you have ASICs, which are application-specific integrated circuits, like the microcontrollers or the chips running, I don't know, in this device or the phone or part of your mobile phone. But these are very much dedicated hardware. So these are designed for a specific task, and they cannot really be changed. So what people are looking at is things like FPGAs or coarse-grained reconfigurable arrays, which give you some sweet spot between flexibility and general purpose behavior. You already seen this slide. So FPGAs are essentially a programmable hardware chip that give you a way of expressing your logic as a collection of gates. And as always, there's a trade-off in that the more logic you try to put in an FPGA, the more space it occupies, and at some point you run out of area that you can use. Okay. So when we think of integration of FPGAs, I just want to quickly, or FPGAs or any kind of accelerator, I want to quickly go through the three options so that you see a little bit the trade-offs. So the most common way that people think of deploying an accelerator is on the side. And this is kind of the way that the GPU, for instance, is deployed, but also how many of the FPGAs are deployed, where your data is kind of controlled or owned by the CPU, and it's explicitly sent to the accelerator, which will do a transformation, filtering, whatever it does on the data, and send the results back to the CPU. This connection here could be PCI Express. But really what is important is this notion of the CPU owns the data and manages it, and then passes it through the accelerator explicitly. The other option is the in-data path acceleration, where the data is coming from somewhere, and the somewhere could be main memory, the network, a disk, and it goes through, let's say, in a streaming fashion through an accelerator, which will either reduce the data amount, change it, transform it, or let's say derive some additional information from it, and then pass it through to the CPU. And then the one that you cannot really see has an orange box here inside the CPU, which is a co-processor model. So saying that actually inside your main processor, there's a small specialized unit which can handle the acceleration functionality. So all of these options are actually present in the wild. So you can today you can see them being deployed. So in the Amazon cloud, you have the F1 machine instance, which has an FPGA accelerator attached via PCI Express. So it looks like a fairly standard underside acceleration. You have the Microsoft Catapult project where they have an FPGA attached to each machine, and the network interface comes into the FPGA, and again, you cannot see it here, but goes out of the FPGA and goes into the network interface card of the machine. Why is this useful? They can offload a lot of the virtual machine related networking tasks here. So things like network address translation, figuring out which packet belongs to which virtual machine, can be done here on the FPGA. Before they deployed this Catapult system, they had to use part of their CPUs to actually do this, let's say, decoding of packets and figuring out which virtual machine takes which packet. So of course, this is in a cloud setting, so the purpose of these machines is to run multiple virtual machines on top. And then finally, we have the coprocessor model, which you might remember from my previous talks. One example is the Intel Xeon plus FPGA platform, where they, throughout the last few years, have been integrating FPGAs closer and closer to the CPU. So first it started as a dual socket machine, and then they moved the FPGA inside, or they will be moving the FPGA inside the CPU. Okay, so you've seen we're at a point in time where specialization not only makes sense, but it makes it can be economically feasible. We have all these different ways of deploying accelerators. We have all these different kinds of accelerators. So, we have, let's say, we are all ready to start implementing things for databases. But what happens is, for reasons that you will see, some people are not very optimistic. And they say, well, this is all good. The time might be right for some workloads, but for databases, it doesn't really work. And one of the reasons comes in different formulations, but this is kind of the purest version of it, which says, like, if you're doing underside acceleration, you're introducing overhead because you need to transform the data so that the accelerator can consume it. So think of things in main memory might have pointers, right? You have virtual memory. If you have to pass it to the accelerator, you might have to actually flatten it or make a copy of these things. You might have to change the pointer so that the accelerator can follow them. So you end up with a lot of overhead. And again, you don't see it here, but what a lot of papers do, and I don't want to name names here, but they implement something on the FPGA, which is, let's say, 2 times faster in compute time than a full CPU. But then if you factor in the data movement overhead, the whole system performs the same way as without acceleration. And then you make the argument, why should I pay money to have an extra specialized hardware in my servers if the final performance is going to be the same? So this is kind of this is one of the let's say the reservations that people have with this deployment. Yeah.
Is there any energy gain there?
So that's also that's an argument that you can make. So you say that this is more energy efficient than the CPU, but it usually leads to it's not a slam dunk, because what happens is you say, okay, this is more energy efficient, but I just paid here for a server. Sorry. So I paid here for a big Xeon CPU, right? Which cost me money. And even if I'm not using it, it will use some energy. So in the end, it's not entirely clear that even though this part is more energy efficient, if I still have to have this thing around all the time, I might as well just use this. So yes, in some workloads you might make the argument, but overall, it's very difficult to sell. So what would be ideal is if you could use this and this always at the same time, because then, or most workloads could take advantage of both, because then you would get a more realistic argument on energy efficiency. Okay, so the second reservation is that, as you remember probably from my previous talks and discussions on FPGAs, is that because you have this behavior that all the code that you express on the FPGA will take up circuit space, and at some point you run out of space, often the algorithms will not be able to handle all the corner cases. So for instance, if you wanted to build a hash table on an FPGA, if you want to only use the FPGA's internal resources, the only option you have is to build a fixed size hash table. You cannot really size it to infinity, right? So at some point you will run out of space on the FPGA, which is, it can be fine for some workloads, but the problem is, or it gives you benefits because you have constant access time and it's very low latency. But if your data doesn't fit, you're in a tough spot because let's say this hash table has 1,000 entries, and if your data happens to have 1,001 distinct entries, then it's not entirely clear what to do. So the problem with this is that in many database workloads, you can derive statistics of the data and you can estimate roughly the cardinality of queries, but you can never be sure. And if you end up, let's say, doing half of your query processing here, and then you realize I messed up because the data doesn't fit here, then you have to restart, or then you have to change the plan, and that can be costly. So this is, let's say, another pain point that people working in query optimizers bring up a lot, which says that having this kind of behavior where your accelerator helps a lot in the lucky case and then performance falls off a cliff in the unlucky case is a nightmare for the query optimizer because you don't really know how to divide the resources across queries. It makes everything uncertain. And then finally, and this is kind of the ugly thing that nobody really talks about, but it's true, is if you look at SQL, it's actually not a very compute intensive thing. So if you look at the analytical queries that people used to write, these are not so, they don't require so much heavy lifting. So there is this paper, the X100, which was I would say, a very important paper talking about the internal structure of databases. It actually showed that at that point, so 2005, in most database engines, less than 10% of the execution time of a query was spent on computing. The rest was spent on things like passing through functions and essentially, I don't know, dereferencing pointers and stuff like this. And then they also found that most of the operations in analytical queries are these ones: summing, subtracting, you know, maybe computing an average, which with all honesty, if you do it the right way in software, you can make this very fast. So around 10, 15 years ago, what happened in the space of analytical databases is people realized that instead of if your goal is to go through large amounts of data and you're not necessarily interested in all the columns, then instead of going through the data like this, like a snake, you know, like reading the row of the first tuple and then employer ID, last name, first name, salary, and then the row ID of the second ID, blah, blah, blah. Instead of going like this, you could actually go column by column and then optimize here everything to, for instance, if you're filtering by salary, then you can make your call graphs shallower. Your functions don't need to be switching between handling or decoding these different data types. You can optimize for one type. So with this, it looks like the outlook is pretty grim for acceleration. If we look at on-the-side acceleration, which has been, let's say, a very common option, historically speaking, there's a lot of overhead, and it becomes murky to say when the acceleration actually helps. Query planning can become a nightmare if if the behavior of the acceleration is unpredictable. And then finally, if we look at some of the workloads that people care about, there's actually not much that you can accelerate. So for the rest of the talk, I will go one by one and try to convince you that actually these reservations are not grounded anymore, and there is, let's say, room for improvement in all of that. So what happens with the overheads is actually these days you have larger machines, you have more data, you have distributed setups, and what we should be aiming at with accelerators is not kind of the on-the-side deployment, but at using accelerators at reducing data movement bottlenecks. So there's many cases where the data is moved anyways, right? So you need to move data from the disk to the CPU or move data over the network. So the goal should be to use an accelerator to reduce the data amount where the bandwidth is high, so that you can utilize better the links or the connections where the bandwidth is low. So one example of this, and some of you might already know this from previous talks, was the IBEX project, where we had an SSD with an FPGA as an SSD controller. And then here you again don't see the database, but here's a CPU which runs the database. And because this is analytical data, back at the time, the data set didn't actually fit in main memory, so you had to read it from the disk, right? You were streaming it from a disk. And then what the FPGA could do is offload parts of the query, of this query tree, right? The query execution graph. You could offload parts of the filtering to the FPGA inside the SSD. And we could do things like projections, so meaning that you remove some of the columns, selection, so that you filter out some of the tuples, and group by aggregation. And in addition, we could also provide kind of value-added services like computing statistics on the data as it's moving here. What is important here is that this acceleration is it's for free in the sense that you have the data coming from here and you have a lot of internal bandwidth inside the SSD, and you have less bandwidth to the CPU. So anything that you can do here, which will reduce the amount of data hitting the CPU, will be beneficial. There's a little bit of added cost of having this FPGA there, but this is, let's say, both energy and the actual part cost is not so high, so it pays off. Now, what happened in the meantime is we did this on an SSD, which was, I think, SATA 2, so 600 megabytes per second. In the meantime, flash or SSDs have becoming a lot faster, and you have now solutions which even reach 3 or 4 gigabytes per second read bandwidth, which makes all these ideas even more applicable and even more interesting. People are, so there's Samsung had some research papers on this, and MIT also had some newer work with faster flash, and they are exploring here different types of near data processing capabilities. What is important, or there's a research challenge in the whole thing. So the choice of this processor is actually important, and I will tell you why. So think of this query here, where we are, looking for some customers who fulfill a condition, and you can see there's different filters that we could push down close to the data, right? So you can do simple things like comparing two integers, but you could also do more complex things like doing regular expression matching. The big research challenge here is that you want to do this in a way that you can ensure that the near data processing never slows down your data access, because these processors are not as powerful as your main processor, right? So if you offload a filtering task, which let's say behaves slower in the near data processing than your main processor, then you kind of undid all the benefits of this acceleration because you slowed everything down. So if you look at software, if you add, so the way to read this graph is you have some throughput target, right? So you want to read data, let's say at 3 gigabytes per second, and then you have no processing here. And as you add different processing options like conditional matching or strings with wildcards, or maybe you're even decompressing the data, on a CPU or in a software style solution, at some point you will become compute bound, and with every extra instruction that you add, you will slow down the system further. What hardware allows you to do, or specialized hardware allows you to do, is to design solutions, and you again can see it, but you will have to believe me, you can design solutions where you can reach the 100% of the desired throughput for all of these cases. And there's no magic involved. Really what you're doing is you're just choosing a different trade-off of things. So you're building a system which, instead of being, let's say, bound on compute resources, is bound on bandwidth, so to say. So this hardware solution will not be able to go any faster than this 100%, right? In software, you often could do things like, if you optimize parts of this processing or you use different processing, you could go more than 100%. But in hardware, you say, I pick this line here, this is my target throughput, and I will design everything around so that I can reach this throughput for any combination of filters. This is important because if you remember in this, like in this case, you have a fixed rate, you have a maximum rate here. So it doesn't really make sense to try to make this part faster than the maximum rate here, because you will not get any benefits. So this is kind of the takeaway message here is you want to have specialized hardware because you can actually, by design, ensure that the performance matches that of your storage. And you can also make the behavior let's say, predictable. So, which brings us to the second point, which is the all or nothing behavior, and you know, how do we deal with this? So here, an idea that both us in our work and other people have been exploring is this idea of hybrid processing. And I will give again with IBEX, give you an example of how this works in our case. So imagine you want to compute the following aggregate function. You want to compute the average salary of each department in your company, okay? So if you look at what IBEX gave us, so we have an input table on the SSD, right? And then we can run through this. You have these operations like projection, selection, and then sending the filter data to the CPU, which could do the group by here in software, right? So the group by being taking all the entries and then putting them in a hash table and summing up their salary. So, okay, in this particular query, there's not much, there's projection going on. So maybe this is the original table, which has a bunch of columns that you don't need. You can filter them, or you can remove the ones that you don't need. In our case, there is no selection in this query, but you could easily imagine that you say, I want the average salary of employees earning more than 1,000 euros and group by department. So you could do some filtering and then send this data to the software. Okay. So now if you remember what we talked about, you could choose maybe to add another acceleration option here, which is about group by queries. So you could make here another block, which now tries to compute the result of the group by on the FPGA. And this can work if you're lucky, right? It works very well because you can build this hash table very low latency and very high throughput. But the problem is, what if the groups don't fit on the FPGA, right? Like this is the example I gave you. You have 1,000 groups here at most. What if you have 1,001 groups in your data set? So what we proposed is to actually have a hybrid processing where you, by having the acceleration here, you don't remove the functionality from software, but you kind of split this functionality between hardware and software in a way that they can work, let's say, together. So in the best case, all the groups are computed here, and what you get here is the final results, and the group by operation will simply look at 1,000 groups and say, okay, I have nothing else to do. But in the unlucky case, this one will evict entries of the hash table, and this group by step will kind of use those to compute the final groups. And the reason why you can do this is that, so for instance, things for average or sum, you can compute the partial sums and add them up later. It will result in the same result as if you would do it in one go. And whether this works, the answer is yes. So in our experiments, and let me explain. So this is MySQL default behavior. And these two lines are IBEX with this hybrid group by. And what you see here is going from 0% bypass. So this means that all the groups are computed on the FPGA and all of the results are sent to the software. To almost all of the tuples have to be sent to the software for post-processing. The performance behaves in a very predictable way, and actually here reaches the same point as software. So this kind of counters this, let's say, worry that people have that the query optimizer will have to pick between all or nothing. What you see here is a very predictable behavior depending on how many groups, how much larger the number of groups is than that you have accounted for in the FPGA. You will have a predictable behavior. And actually, what happens in case of MySQL, we implemented here. This is our optimized software plus hardware implementation. So we replace the default group by of MySQL with a custom implementation where we optimize for a smaller number of groups that you have to do in software. So this is just to show that if you kind of change a little bit the assumptions, you can get more speed up by optimizing the software as a result. So I think this was a nice example of with hybrid processing, you can actually start by adding in a hardware element, which has this kind of no worst case slowdown guarantee. And then depending on what you see there, maybe you can again optimize your software as a result, because now you have less, on average, you have less data to do in software, so you can use the caches more efficiently, so on and so forth. Now, in the case of the group by, this was a very, let's say, simple way of splitting the functionality or dealing with corner cases, because you could always use the same kind of operation again to compute the final groups. But I think this is a very interesting line of research, more generic or in more general terms. How do you split functionality between different devices? This is, of course, this is between accelerator and software, but even the question of how do you distribute, I think people, maybe even in this room, have looked into this problem of if you are moving from a single machine implementation to distributed setup, how can you actually kind of cut ties in the algorithm, in the processing, in a way that the whole thing works in the end. Okay. So on the first two, I hopefully convince you that there's, let's say, the problems are not fundamental, and by looking at the right way at the problem, so putting the FPGA in the right place, or by combining software and hardware in a hybrid way, we can actually overcome them. And then finally, what happens is, for the compute-intensive workloads, actually recently there has been a lot of change going on. So if you look at analytics workloads and analytical databases, their offering has been increasing, and they all offer more and more involved data analytics packages. So this here, you cannot really read it, but this is a list of operators that SAP HANA offers, which goes from there's classification, regression, clustering, time series, association, probability distribution. So you can see slowly there's operators making their way into the database, which look more like, let's say, something that you would use in machine learning, and people want to use this. So this kind of brings a lot of compute-intensive operations into the database, which you can accelerate. And what happens is, here I'm just highlighting two projects from people back at ETH, where they show that you can actually use FPGAs in kind of novel ways, both for building models inside the database. So if you want to use your data to create some kind of classifier, you can do that, or to run inference later, you can also rely on hardware. I don't have the time to talk about this, but you can even take classical, so to say, classical boring algorithms like k-means clustering, and use this kind of ideas of hybrid processing and in-data path processing to accelerate it and give benefits to the database. Okay, so we've seen these challenges, and it looks like we have to be optimistic, because we have a lot of data movement in the data center. So we have a lot of places where we could put accelerators. We have, let's say, our work cut out for us as researchers to figure out how to split algorithms between hybrid devices. But this is, again, something that will lead to benefits in the database. And then finally, it looks like there's enough workloads emerging that all of this acceleration will make perfect economic sense. So the question is, are we done? Is this it? So can we pat ourselves on the back and then just do what we have been doing until now? So I believe not quite. And there's I just want to kind of show you two directions where I think a lot of work still has to be done. And this is something where I think this is where the most of the interaction could be between people like myself and people like yourself working in other fields. And one example is the question of compiling or synthesizing these hardware accelerators in a more flexible way. So what happens these days is people write these accelerators from scratch, right, by hand. But maybe there's better ways of doing this. So one question from the database perspective is, is there a way to take a user query and try to figure out, maybe even synthesize the accelerator from that particular query? That would be something that would definitely increase the applicability of these accelerators if the database could actually take part of the query execution graph and put it into hardware on its own. As a fallback, and this is what I meant here by designing a set of specialized cores, you could imagine that maybe what happens is that the service providers will provide you 10 kind of building blocks that you can use, or 10 accelerator units, and then simply you will try to match your database query plan onto these 10 blocks. Of course, for me, it sounds more as a research question to try and figure out how we could go from a high-level user query to actually generating hardware circuits. And I think this is where DSLs come in. So if you think of this per-execution graph I showed you, the physical plan, right, of how do you do filtering, joining, which algorithms you choose, actually internally they have, let's say, a lot of operations repeated. So you have building blocks like, you have to hash data into some small hash table, you might have to sort parts of the data, or you have to shuffle things around. And I think, to me, one feasible way of going from a high-level query to actually synthesize hardware is not to try and do a fully custom mapping, but instead use some kind of fine-grained building blocks to assemble these into a circuit. So I think if this is something that sounds interesting to you, then please come talk to me, because I think in this space there's a lot to be done, and it's only, let's say, emerging now. And then the other aspect, which I find very challenging, is the question of how do we actually manage and how do we, let's say, share these accelerators in the cloud. So the management is maybe less interesting discussion here for this audience. The question is, do we let the operating system or hypervisor to manage the FPGA or the accelerator, or do we want the database to do it on its own? But beyond that, I think from a design perspective of how do you design acceleration functionality, you have this point of, at some point you will have to end up sharing the hardware, either because you have multiple virtual machines running in a physical server, or either because you have multiple queries inside the same database engine using the accelerator, you will have to end up sharing the circuit. And then you have issues like, how do you isolate data belonging to different tenants, maybe? Or how do you isolate the performance of different queries running on the FPGA? And just to give you an idea of what's in this space, a lot of people are proposing things like virtualizing these devices, which is very general purpose solution. So you cut up, you partition the space on the FPGA, and then you put the different blocks here. What happens is this gives you few tenants, because you can only cut the FPGA into so many pieces before the pieces become very small. You can replace here tenants with, let's say, accelerators, right? So you could have here, let's say, 3 different accelerators. And there's a trade-off, because by making these blocks smaller, there's less functionality that you can offer, and also leads to very coarse-grained resource allocation. What can be imagined in this space is you have an FPGA or an accelerator which is partitioned like this, and then in principle you could let the tenants, or you could use the workloads to bring their own accelerator. So if the query needs here a filtering operation and the other one needs a join, then you could put it here in this box. If it fits, you can put your own, and you use that, right? The problem with this is if you need one more tenant, or if you need a different trade-off, you cannot really have it, because you have cut up the FPGA in some particular way, and that's how you're going to use it. So an alternative, the one which I, let's say, have been pushing in some of my work, is to actually design circuits in a way that they allow for multi-tenant or multi-query or multi-purpose use. So the idea would be to combine elements here in a way that they can handle different types of queries or different types of tenant workloads, and then execute different, let's say, pieces of data belonging to different tenants or workloads on the same circuit. And this is much more domain specific, because you cannot use here in this block, you can put anything inside. You could put here a machine learning operator and here an image processing operator. Here, of course, all these blocks will belong to some domain. So maybe this is SQL acceleration. However, it gives you the possibility to execute for many different tenants, because you're not dedicating resources for each tenant. In software, so if you think of this kind of layout, you have this in software for things like platform as a service, if you're familiar with it, like Salesforce is running many tenants workloads on the same database, right? In software, it usually leads for degraded performance, because for every tenant that you put in the system, you will have a little bit more CPU cycles that you have to dedicate, and at some point you will slow down everything. Actually, in hardware, this is not entirely clear that is the case. With some examples that we explored, you can show that you actually have no degradation of performance. Even so, if you have a single tenant, you can run at, let's say, 10 gigabit speed on the FPGA, and if you have 10 tenants, then each of them get 1 gigabit, and there's no wasted overhead. And this setup also leads to fine-grained resource allocation, so you can actually, let's say, really balance how much each tenant gets. So yeah, this is just to give you an idea of, you know, when you think of acceleration, beyond the question of what do you put inside an accelerator block and how do you wire it up to the larger system, there's other research challenges like figuring out how do you actually share these devices, how do you manage them, how do you bring this block, is this something that the query will determine or is this something that the service provider gives you, and so on. So with this, I want to wrap up and then maybe discuss or answer questions. So hopefully we are all on the same page that the outlook is positive, but there's also challenges, and I think very interesting challenges remaining in order to make this, let's say, really practical and economically feasible. So yeah, I'm